The ferry ticket office scenario is an example of the MM1 model. How do I know that? I'll show you in a second. But if you have downloaded the note frames to work on this problem, you actually ever so conveniently have those formulas included in the back. Now, otherwise, you'll have to look them up in a book. Now, how do I know, other than the fact that the formulas are included in the note frame, that this is MM1? Let's look. Customers arrive at a ferry ticket office at a rate of 14 per hour on Monday mornings. So we have random customer arrivals. This can be described with a Poisson distribution. Okay, that's my first hint because the MM1 model assumes a Poisson distribution. Selling the tickets and providing general information takes an average of 3 minutes per customer and varies exponentially. That was my other hint. The MM1 model assumes that the service rate is exponentially distributed. One ticket agent is on duty on Mondays. That was the last hint that I needed because the MM1 model assumes that there's only one server, and sure enough, there's the one ticket agent to help the customers. Oh, all right. Now the MM1 model, there's a series of questions here, but the MM1 model is just, it's a bunch of formulas. It's a bunch of formulas. Why don't we just look at the formulas before we look at these questions? That you can learn different things about the system. In this case, the ferry ticket office. System utilization, average number of customers in the queue, like waiting for tickets and whatnot. Now notice in each case, you do need 2 input parameters. So that's kind of basically our next task before we touch any of those questions. We need to find lambda because you see it everywhere. Lambda is the mean of the customer arrival distribution. And I think we were quoted lambda actually. Let's take a look again at what a number I skipped over. It says customers arrive at the ferry ticket office at a rate of 14 per hour. Perfect. That's lambda in our case. So I'm writing that here because that will be handy. And then we need mu. You see that also everywhere. Mu is the mean of the service distribution. It is basically lambda's cousin or sibling. And I'm writing something here in ink before I write a number because this is very important to remember. Okay, so mu, we say, oh, well, that's the mean of the service distribution. And you're thinking, oh, yeah, fine, I see that actually in this problem right here because it says that selling tickets and providing information takes an average of, mean average 3 minutes per customer. So, right, you just don't write a 3. Do not write a 3, especially not in ink right there because mu is not 3. Mu is always the average number of services that can be provided in a certain time interval. You say certain time interval, what time interval? Whatever time interval lambda was talking about. Now notice our lambda is 14 per hour. That's just what the scenario said. That means that our mu should be so many services per hour. Now, we said, well, it doesn't say anything about how many tickets you can sell in an hour. No, it doesn't, but right, the 3 is relevant. It's just that mu does not equal 3. If you put a 3 in here for mu, none of this is going to come out correctly. We just have to use a little logic to figure out what mu must be. There's 60 minutes in an hour, and each ticket sale, so to speak, takes 3 minutes. So logically, we could serve 20 customers an hour at the ticket office. That's mu. That's the number that we're going to be using once we start manipulating these formulas. Oh, all right. Now, speaking of manipulating the formulas, what are the actual questions here? Okay, first part. What is the average length of the line on Monday mornings at this ticket office? How am I going to find that? That is capital L for length of the line, lowercase q for Q. Q is another word for line. You see that right there, front and center in the formula sheet. Average number of customers in the queue. There's the formula. I'll just copy it here for reference sake. Lambda squared divided by mu minus lambda. Fill in that formula. That will tell you the average number of people who are waiting to buy a ticket on Monday mornings. Okay, so we said that lambda was 14, correct? So the numerator would be 14 squared. The denominator is 20 times 20 minus 14, or 6. On my calculator, I see 1.6, like 33333. That's the answer. We found out something about the ticket office on Monday mornings. When one agent is there, on average, there's about 1.6331, one or two people there waiting to buy a ticket. Okay, next question. On average, how long does a customer wait to buy a ticket? Wait to buy a ticket on Monday mornings. Now, waiting, if you want to relate this to that formula sheet, is capital W. You will notice that, let's look at the formula sheet again. There's two different waiting time formulas. They're over here on this sheet to the right. Waiting time in the queue, WQ, and average length of visit to the system. Right? Now you say, well, wait a minute, what's the difference in terms of waiting and delay? This one is just how long you wait to buy a ticket. This is the total amount of time that it takes to obtain a ticket, so it includes waiting and being served. What did, and this can be a key to success with these type of questions, which one exactly did this question ask for? How long does a customer wait to buy? So it doesn't include buying the ticket, so it is WQ. Now WQ is LQ divided by lambda. So if you have done this on a calculator and you're still looking at this displayed on the screen, quick, we need that number, just say divided by 14, right? LQ divided by lambda. And you'll see something like 0.166666. A lot of repeating numbers in this particular problem. Oh, that's the answer. That's the answer. It's not in a very helpful form right now, because what is this supposed to mean? We're talking about on average how long you have to wait to buy a ferry ticket, and it's 0.166666 hours. That is in hours. How do I know that? Whatever lambda and mu we're talking about, your W formulas return you an answer in those units. Okay, so the average wait to buy a ticket here is 0.11666 hours, which isn't very intuitive. Now, we can translate that very easily into something that makes more sense. You could take that, matter of fact, if it's still showing on the screen of your calculator, just multiply it by 60. There's 60 minutes in an hour. And you may see like 6.9999999, but basically you are looking at 7. And we are looking at an average of a 7-minute wait to buy a ticket at this office on Monday mornings. Okay, next question. How long does it take to successfully buy a ticket on Monday mornings in minutes? In minutes too, right? So it's good that we are translating this to minutes. This includes, now see, this is trying to help you out with that decision of what formula to use. This includes waiting in line and purchasing from the agent. Oh, so this is the other formula. This is not WQ, this is WS, the total amount of time spent in the system, which is not unrelated to the total amount of time spent in the line, WQ, because you take that and you add 1 over mu, and that will get you the total time in the system. Now, in doing this, careful. Remember that these formulas all talk about hours, so what we want to put here is the old unintuitive 0.166666, because we're going to add to that 1 over, now let's see, mu was 20, or 0.05. So that comes out to like 1.666667 hours. I mean, it's a true statement. You need to buy a ferry ticket. On average, it's going to take you in total 0.166667 hours. Again, it even asks us that in minutes, so no problem. Now, on your calculator, times 60, take that, times it by 60, because there's 60 minutes in an hour, right? And that will reveal like 9.9999999. It is 10 minutes. So if somebody dropped you off at the ticket office and you asked them to wait, like at the curb in the car, because you'll be right back out, it'll take you an average of 10 minutes to get back to them while they wait on the curb. That's total turnaround time. Oh, and in this case, you know, it was important. These formulas are all working in hours because lambda and mu are in hours. So to work that formula, you put the 0.16666 in for WQ. But you can see that there's actually another way to do this. It is not a coincidence that we figured out the average wait in the line was 7 minutes. And if you go all the way back up to the original statement of the problem, we were told that the average service time is 3 minutes. 7 plus 3 is 10. That's not a coincidence. That is like another way to find that particular answer. Okay, now we're not done with questions though. What is the probability that an arriving customer has to wait to buy a ferry ticket on Monday morning? The key to this question is realizing what is it the equivalent of in terms of the official description of the formulas. The probability that you'll have to wait, maybe I'll write that down, probability of waiting. We're not even talking about how long. We're just saying what's the probability you actually have to wait, is the same thing as the probability of the system being busy, in essence. Because if you walk up and it's busy, the ticket agent is busy, that means you will have to wait. That is known more formally as system utilization. The proportion of time that the ticket agent is busy is very easy to calculate. It's right there. The proportion of time that the ticket agent is busy is the system utilization. And in order to determine that, the only thing that we have to do is say lambda divided by mu. So in our case, that's what? 14 divided by 20. So that's like 0.7 or 70%. That's the answer to the question. The probability that an arriving customer has to wait at least some amount of time is 70%. That is also the amount of time or the proportion of time that the ticket seller is busy. Now, last question. What is the probability of exactly 4 customers in the ferry ticket office? This includes both customers waiting in line and being served. We have a tool for that. It's over here. See it? Probability of n customers in the system, right? You pick a number. This particular problem is asking about 4. I better copy that formula over here so we can look at it. The probability of there being exactly n customers in the ferry ticket office is the probability that there are no customers, that is p sub 0, times lambda over mu to the power of n, whatever the number is that we're interested in. Oh, now wait a minute. If we're going to figure it out for n equals 4, we need this. We're like, what's this? Oh, that's another formula. The probability that there's nobody in the system is, and you can find it on the formula sheet, 1 minus lambda over mu. It's actually the opposite of that right there. So the probability that nobody's in the system is 0.3. Right? Because if there's a 70% chance you have to wait, there's a 30% chance that you won't have to wait. That's the chance that when you just show up, there's nobody in the system until you step through the door. Now, okay, wait, that's not going to answer the question. That's a means, but we're not there yet. We've got to answer the question, what's the probability, like you just show up, you haven't stepped through the door yet, and there's exactly 4 customers. We'll fill in the formula. Okay, so that would be the 0.3 for the probability of nobody, times same old 14 divided by 20, or 0.7, we figured out before, to the power of 4. So what you would want to say is, 14 divided by 20 is 0.7. You'd want to say 0.7 times 0.7 times 0.7 times 0.7. Oh, then times 0.3. That's where I'm getting 0.072 by the time you're done, which is, you talk about probabilities, it's more intuitive to turn them into percents, about 7.2%. So you turn up at the ticket office, maybe you're going to buy a ticket, maybe you won't, but you turn up in the doorway, there is about a 7% chance that there'll be exactly 4 customers in the office on Monday morning.